Okay guys, today we're going to start 5.4, the definite integral and summation. Today we're just going to get through the summation part. This is technically 5.3. I've just included it into 5.4 as it makes the most sense. The homework for this lesson is a worksheet that has been copied but has not been handed out yet. The worksheet is online, so feel free to look at it to get what you need. First we have some theorems. Summation notation. The summation of from k equals 1 to n of ace of k is equal to ace of 1 plus ace of 2 plus ace of 3 plus all the terms necessary to get to ace of n. Notice our counter here went from k equals 1, thus ace of 1, to k equals n, thus case of n. Now, theorem 510. The summation from k equals 1 to n of a constant number c is simply n times the constant. Think about it. If we have the summation of 5 from k equals 1 to 3, that means that this is our term. So we want it the first time plus the second time plus the third time. Therefore, we have 3 5s for our summation. Now, there are 3 other summation rules. These rules were proven by some very smart mathematicians, most notably Gauss. Friedrich Karl Gauss loved summation. He loved learning how to count things out. He's the one that made up most of these formulas that we work with. And he did a lot of this work starting at the age of 8 all the way until his entire career. Basically, summations work just like integrals, just like derivatives. You can break summations up over their sum. You can break summations up over a constant multiple, and you can break summations up over a difference. The formulas are down here in theorem 512. The summation of a number from 1 to n of k, where k is some counter, like 1, 2, 3, blah, blah, blah. This is the sum of the first n integers. It is n times n plus 1 divided by 2. I'm going to offer you guys extra credit if you can show proof as to why this works. I will tell you that this is a theorem that Carl Friedrich Gauss discovered at the age of 8 in his classroom when he made his teacher mad for not listening to his teacher. None of you have that excuse for making me mad when you don't listen. He had an excuse because he came up with a very important theorem right here. The next is a summation of k squared. That's a term squared. It's 1 squared plus 2 squared plus n squared, yada, yada, yada. It is n times n plus 1 times 2n plus 1, all divided by 6. The last one is summation from k equals 1 to n of k cubed. It is 1 cubed plus 2 cubed plus yada, yada, yada plus n cubed, which is equal to the quantity n times n plus 1 divided by 2, quantity squared. So let's try some summations. Here we have a summation. This summation is a product. It's a summation of k squared times k minus 3. We don't have any summation rules for a product. So just like our integrals, just like our derivatives, we want to try to break it down. Sorry, that is an equal sign. Microsoft Word does not always like to write summations correctly, so I apologize. So let's write this out. We have the summation from k equals 1 to 4. If we were to expand this out, of k cubed minus 3k squared. Now here's something that's very important to note. Right now, our summation merely is modifying that k cubed. A summation cannot modify an entire difference. It just modifies what is immediately touching it. In this situation up here, our summation was modifying that product, which meant it had the whole thing, so it was good. But here, not so much. So what we need to do to make sure that we know our summation is modifying that entire sum or difference is we need to put parentheses all around it. Okay, is it just me, but that win on the screen, I don't know if you guys can see it, but it's starting to really bother me. Anyway, we have to do the parentheses to know that our sum is modifying the entire difference. So now let's use our basic summation rules. We are going to have the summation from k equals 1 to 4 of k cubed minus the summation from k equals 1 to 4 of 3k squared. Just like with integrals, just like with derivatives, we can pop the 3 out. So we have the summation from k equals 1 to 4 of k cubed minus 3 times the summation from k equals 1 to 4 of k squared. Okay, so looking at this, what we have going on is we can use our formulas now. Remember, for k cubed, it's n times n plus 1 divided by 2, that entire quantity squared. Here, our n is 4. So this term right here is going to be 4 times 4 plus 1, all divided by 2, quantity squared. Here we have a k squared term. Remember, k squared is n times n plus 1 times 2n plus 1, all divided by 6, so minus 3 times that quantity. Our n still is 4. So 4 times 4 plus 1 times 8 plus 1, all divided by 6. Now we enter this into our calculator to see what we get. So 4 times 5 divided by 2 squared is 100, minus 4 times 5 times 9 divided by 6 times 3, minus 90 gets us a grand result of 10. What do you think? Not that bad? Okay. Here's a summation of 2 to the kth power divided by the quantity k plus 1 from k equals 0 to 8. That's 2 to the kth power. So there truly is no way to just use our formulas on this one. So, and again, there's also no quotient rule, so what would be nice is if we could somehow break it over the quotient, use our formula on k plus 1, and that'd be n times n plus 1 divided by 2 for n equals 8 plus 1. But that's not going to work because we do not have a quotient rule. So for this one, we have to evaluate for what is it at k equals 0? What is it at k equals 1? What is it for k equals 2? K equals 3, 4, 5, 6, 7, and 8. The easiest way to do this is to put it into your y equals 2 to the x power divided by the quantity x plus 1. Go to your table. We should be hopefully in table set mode where we can type it in, or at least just start right away. So when k equals 0, we get 1. When k equals 1, we get 1. When k equals 2, we get 1.3 repeating, which we all know is 4/3. When k equals 3, we get 2. When k equals 4, we get 3.2. That is 3 1/5, or 16/5. K equals 5, we get 5.3 repeating, which is 5 1/3, which is 16/3. K equals 6, we get 9.1429, so I'm going to actually put that into the entry part. So we get 64 divided by 7, which cannot reduce. So we get 64/7. K equals 7, I'm seeing 16. K equals 8, I'm seeing 28.4 repeating, so 28 4/9. 28 4/9 is 28 times 9 plus 4 is 256 ninths. Okay, now all we need to do is we need to take this entire column we just found of values when we substitute in k, and we need to sum them up. So if we sum up those values, 1 plus 1 plus 4 over 3 plus 2 plus 16 over 5 plus 16 over 3 plus 64 over 7 plus 16 plus 256 over 9 gets us 67.454 and change. Math frac that. We get 21,248 divided by 315. There we go. Next example. Evaluate the summation from k equals 1 to 100 of k and from k equals 1 to 20 of k squared. Recognize that we use the formulas. Here our formula is going to be n times n plus 1 divided by 2. So it's going to be 100 times 100 plus 1 divided by 2. Remember, this is the formula that I'm giving you guys the extra credit for to prove it generically for me. Provide me a proof. Don't just Wikipedia it. Don't just Google it. Whatever proof you get me, you must be able to also explain and justify. You can regurgitate anything you find online, but what you hand in for extra credit must demonstrate some understanding of the mathematical principles involved. Therefore, if I question you on what you turn in, you can give me some sort of intelligent answer. So 100 times 101 divided by 2 is going to get me 5,050 for this sum. Okay, the sum from k equals 1 to 20 of k squared. Use our k squared formula, n times n plus 1 times 2n plus 1 divided by 6. So n is 20, n plus 1 is 21, 2n plus 1 is 41, all divided by 6. So that's for this guy. So 20 times 21 times 41 divided by 6 is going to give us 2,870. One moment, guys. Sorry, I just want to check that this was the last example, which it is. So what we have going on here is to get this in terms of n, which we can do. Notice, I have a nice, big, beautiful set of parentheses around this polynomial, which means my summation is modifying the entire polynomial. I like that. So first thing we should probably do is know that A, you can break up the summation. We can have the summation of k squared minus 4 times the summation of k plus the summation of 3. Now, all these summations are running from k equals 1 to n. So that's something to keep track of, something to make sure that we also do not get sloppy as we write out our work, because sloppiness can lead to inaccuracy. So our k squared formula is n times n plus 1 times 2n plus 1, all divided by 6. Our n formula, so minus 4 times n plus 1 divided by 2. Our 3 formula is 3n. So now we need to expand this. So here we have n squared plus n times 2n plus 1 divided by 6. Minus 2 goes away, that becomes a 2 minus 2n times n plus 1 plus 3n. Any questions so far? Make sure to make a note of it so you can ask tomorrow. Expand that product of binomials. We're going to get 2n cubed plus n squared plus 2n squared plus n, all divided by 6, minus 4n squared minus 2n plus 3n. Okay, looking at our terms now. N cubed term is the only one right here. That is 1/3 n cubed. N squared terms, we have 3n squared divided by 6, which is 1/2 n squared, minus 4n squared would be negative 7/2 n squared. Looking at the n terms now, we have 1/6 n plus n, so we have plus 7/6 n. And there is our expansion. Okay, this is everything you need to know on summations. There are 10 problems in the 5.4 worksheet on my website about summations. Look at them. You do need to know these formulas. Last reminder about the extra credit. If you can show me Carl Friedrich Gauss's proof of the summation of the first n integers, ideally you should be able to discover it by yourselves. Just use your intuition. Look at the pattern. Think you know the answer. Write out maybe 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Look at that and think, how could he have gotten to that basic formula doing what he did? If you do need help with your resources, that's fine, but I will, one at a time, quiz you individually, orally, kind of like an oral comprehensive exam, to see, can you explain to me, can you demonstrate understanding of why that works the way it does. If you really want to expand it to the other two, more than happy for you to try that. So definitely, if you want to try the other two also, feel free to show what you know. Have a great rest of your snow day. I'll see you tomorrow when we finish 5.4 and integration.